thank the participants, for the organizers for organizing this. I think it's a very nice meeting. And I also want to thank them for giving me the opportunity to give you a broad review of what holography can do for you. So instead of focusing too much on specific applications, I want to tell you a few things about what you can actually do with holography, what you cannot do with holography, and the general ideas and the kinds of problems that you can think about solving using holographic techniques. I will not focus too much on specific applications because I think you will be probably bigger points about it. But feel free to talk to me and we can discuss if you have some application in mind. So the talk is divided logically in a few sections. So first I will try to motivate holography and why you might want to use it. And I will also explain not only why holography, but also a bit how holography manages to solve these problems for you. And then I will talk about the anti-de Sitter boundary, which is a geometric place where we think about the dual field theory, and I will explain what ADS is and what the boundary of ADS is and why it is important in holographic techniques. And I will also just tell you a bit about the holographic dictionary, how you translate between things that you read from geometry to what it means for a field theory, and how do you read off field theoretic quantities. Then I will talk about how holography geometrizes states of field theory, thermal states, RG flows, ground states, not ground states, and we will see pictures of them. And then I will use these pictures to discuss RG flows that you can study with holographic techniques, finite temperature, and what the black brane is, and how black brane is used to geometrize a finite temperature state in field theory. Then I will talk about real-time dynamics, and then my talk will be divided between near equilibrium. That will give us quite a bit of intuition about what you can ask in holography. I will talk about linear response, the emergence of hydrodynamics, and also transport coefficients and how the transport coefficients are encoded in geometry, how you can read them off. And then, far from equilibrium, this is non-linear stuff and non-linear study. You can ask many different questions which branch out to completely different directions, but I have chosen 3 questions about thermalization, the emergence of hydrodynamics, and driven dynamics, non-linear driven dynamics, which I guess are of broad interest to anyone who is interested in field theories and quantum mechanics. Okay, good. So why would you want to use holography? Well, holography is about systems which are very strongly coupled. To be honest, infinitely strongly coupled. So the simplification that comes from holography, which turns everything into classical gravity, is in the ultra strong limit of specific classes of field theories, the infinite coupling limit of field theories. So in these regimes, usually perturbative techniques fail to give you answers to questions that you might want to ask, to interesting questions. And so, and similarly, the lack of quasi-particle description of these systems will not let you build, some kind of perturbative or effective model that would let you study such systems. And holography is very efficient in doing that because you don't have to make any assumption. You can just study the system as is without building any effective theory. You can extract effective theories from it by taking a low energy limit, but you don't have to. You can do the full microscopic calculation and you will get an answer. So what holography does for you is that it takes non-trivial questions about real-time dynamics. You might want to ask, a strongly coupled field theory, what will happen to the system if I introduce some very strong time-dependent source to the system? And that's a very difficult question to ask in quantum field theory. However, holography simply turns this question to just solving PDEs. Okay, you would have to solve Einstein's equations in some space-time with specific asymptotics. It's not always a trivial question to ask, but it's just PDs. We know what to do with them, given that you have, I don't know, efficient numerical techniques, or if you're a very strong mathematician, you can just go and ask these questions. I mean, it's well-defined questions that we have techniques in order to answer them. And so all of these questions can be turned into problems in classical gravity through holography, which you can just go and try to solve. So now the question is, I mean, I will just tell you how the dualization happens, but how do you ask the question in holography, and what kind of problem you have to solve. So how is this achieved by holography? Well, holographic theories are usually, holography describes large classes of conformal field theories, which have a specific, well-defined large n, and at the same time, large strong coupling limit. So n, I mean, imagine that you have a gauge theory, which has an SUN group, or n by n matrices. And when you take the size of these matrices to be very large, and at the same time, you take the coupling to be strong, then in that limit, these theories become semi-classical. There is a well-defined semi-classical limit. And what holography does for you, it tells you that effectively, the classical description of these theories is gravitational. Okay? And the dictionary turns field theory questions into just questions of classical gravity. Now, the caveat is that this, as I will explain, and I will sketch maybe, the dual gravitational theory lives in one dimension higher. Okay? There is no way that you can take a field theory that lives in d+1 dimensions, and you solve a gravitational system in d+1 dimensions, and that is dual to your field theory. The gravitational theory will have to be d+2 dimensional. There is an extra dimension. This is why you call it holographic. There is an extra dimension added to your system. So this additional radial direction, as I will tell you, or as I will try to explain, you can think of it as an energy scale of the system. Okay? And the theory that you're studying is to be thought as the UV limit of that energy scale. Okay, so let's start discussing symmetries and how this extra dimension emerges naturally for a conformal field theory. So before discussing conformal field theories, let's talk about relativistic theories. Okay, so relativistic theories will live in a Minkowski spacetime, which has d-1 Euclidean directions and an extra time direction. If I want to define a metric where the field theory lives, this is, I hope this is familiar to most of you, this metric. This is the Minkowski metric in d-1, 1 dimensions. Now, the symmetries of this metric, or the symmetries of any field theory that is relativistic, will be SO d-1, 1. So this d-1 reflects the d-1 Euclidean directions, spatial directions, and the one reflects how many time-like directions you have in your field theory. And so this group is basically a group of coordinate transformations which leave the form of this metric invariant. Now, apart from these rotations, these are like rotations. In Euclidean space, I would just write, SO3 if I only had rotations in 3 dimensions. Apart from these rotations, which are the Lorentz transformations, you also have the translations, and translations together with the rotations form the Poincare group. These are all the symmetries that you can ask for a relativistic theory. Now, conformal field theories have some extra symmetries. One of those is scaling. You basically scale both the time and the spatial direction. And the reason I'm writing this is that this is no longer a symmetry of the background metric. So there has to be a non-trivial transformation of your fields that will compensate for the lack of symmetry of the metric. Okay, so your fields will transform non-trivially. Even the scalar fields will transform non-trivially under scaling transformations. So the metric is not left invariant, and scaling is not a symmetry of the Minkowski metric. For relativistic theories, when similarly to the scaling transformations, they do not preserve the metric as well. They will introduce an extra scaling factor when you do this transformation. So then comes the question of, so this is the conformal symmetry group, right? So you have Lorentz transformations, space-time translations, scaling, special conformal transformations. I still want to think of this geometrically. Can I think of it in terms of a space-time that is invariant under such transformations? Okay, so I want somehow to understand both scalings and special conformal transformations as symmetries of this space-time metric. I don't want it to change like this. So how can I think of this in terms of group theory? So if I take my Poincare group that I discussed about and you have in any relativistic field theory, and I combine it with scalings and the special conformal transformations, then what I see is that the conformal group can be thought of as an SOD, 2 symmetry group. So if I go back, SOD, T, 2 is basically like having a Minkowski spacetime with D spatial directions and 2 extra time directions. Okay, this is just as a mathematical concept. We will not have a spacetime with the directions. I'm just thinking of a space that will respect these symmetries. So how can I geometrize now this symmetry group? I mean, how can I find a space which has these symmetries as a symmetry? So if I follow what I said and I write a space-time which has 2 time-like directions and D space-like spatial directions, then what do I know about this space? Well, it is definitely preserved by the SOD, 2 symmetry group, but I also have translations in U, V, and the XDs. So I'm getting something extra. Okay. So like in a 3-dimensional Euclidean space, you have 3-dimensional rotations, but you also have translations. How do you only keep the rotations? Well, you basically put a sphere. A sphere will only be preserved by the rotations, but not by the translations. So if I take a hypersurface inside this space, which looks like this, it will not be preserved by the translations, but it will be definitely preserved by this kind of rotations, by the conformal group. So this is a way that you can come up with a space that is preserved by the conformal group. Now, this space-time is D plus 2-dimensional. I'm also introducing a constraint, so I'm turning this space-time to D plus 1-dimensional. So immediately you see that I need an extra dimension in order to realize the conformal group as a symmetry group. So this space is precisely what we call the ADS D plus 1 space, anti-de Sitter space in D plus 1 dimensions. Okay, so how can I think of this surface now? Well, I can solve the constraint by introducing some clever coordinates here. This is very similar to how you would parameterize a sphere, but I have these extra minus signs. And so instead of a cosine, you will see hyperbolic cosine and hyperbolic sine. Okay. Now, this Ni is parameterized just as D minus. Because as you see, this coordinate tau is periodic. So if I go from 0 to 2 pi, I will end up at the same point in the UV space. That's a problem. That's a closed time-like curve. We don't want this. So, but there is still no problem writing down this metric and opening up tau. Okay, there is no singular point for this U1 symmetry. There is no fixed point. So I can take tau now to be non-periodic. That's called the covering space. Okay. So tau is now, or t, I will turn tau to t, and that is a real time coordinate. It goes from -infinity to +infinity. Now, this metric written like this is called global ADS. You are covering the full ADS space. As I told you, this metric does have SOD, 2 as a symmetry group. It's not obvious at all. but you can do it. Okay. Now, there is an alternative way to parameterize this metric. I can introduce slightly different coordinates. Please don't pay any attention, don't try to solve the constraint. I'm just writing the transformation there. But this coordinate system only covers half of ADS space. You're not covering the full space. However, in these coordinates, it looks slightly better. I mean, if you want to recognize the SOD,2 group. So the extra coordinate, there is this radial coordinate R. Okay. You can probably recognize here the D-1, 1 dimensional Minkowski space. And there is also this extra radial coordinate that I promised that will be there. So in this coordinate system, or in the Poincaré patch, as we call it, you can immediately see the symmetries of the D-1, 1 dimensional Minkowski spacetime. And you can also see the scaling symmetry, right? So if I scale the x coordinates, I also have this extra radial coordinate that if I scale it with lambda to the -1, it will compensate for the extra factor that you would normally get from this Minkowski space, Minkowski metric. So this is a geometric, I mean, in these coordinates, it's much clearer, but you do get the full conformal symmetry group. And because of this scaling, you already see that, you know, this extra coordinate, the radial coordinate, might play the role of an energy scale in the system. Now, I want to talk about the ADS boundary. So if I do a clever coordinate transformation for this radial coordinate, I take large values of the radial coordinate. Then what I can do is that for the case of global ADS, I will have asymptotically something like this, which is time, a sphere, and dz squared, which is basically the radial direction. And I will also have this scale factor that goes to infinity as I'm taking z to 0. This is for global ADS. This is for Poincaré ADS. Now, if I did not have this extra factor, then there would be no boundary. Because I have this extra factor that blows up, then, you know, this place where I take z to infinity or r to infinity, you have to think of it as a time-like boundary of the spacetime. So there is definitely a boundary on ADS space. Unlike Minkowski space, where there is no boundary, you have a very different asymptotic region for ADS space, and that will play a crucial role. Okay, so you do have an asymptotic time-like boundary. So that boundary is basically where your dual field theory lives. So if I study Poincaré ADS, then I'm thinking of the dual field theory living on this Minkowski spacetime. If I have global ADS, then my field theory lives on a funny spacetime, which is basically the product of time, you know, the time-like direction, and the sphere. So I have taken my field theory and I put it on a sphere for some reason. Now, we will be mostly interested in field theories for this talk that are defined on a Minkowski spacetime. So if I want to draw a picture of ADS, what can I do? So if I think of this as a leaf, this is Minkowski spacetime, then I will just populate the bulk of the geometry with leaves of Minkowski spacetime, and I will also scale them with a radial coordinate. Now, the boundary of the spacetime is basically this leaf, which is somewhere at infinity. Okay? And this is precisely where your field theory lives. So what is ADS, after all? What is anti-de Sitter? Well, it is a space which is invariant under the conformal group. So from now on, you can probably think of this geometry as the ground state of your system. So the ground state of a conformal field theory would be invariant under a conformal group. And similarly, from the geometric point of view, ADS would be just your ground state. Okay, that would be the geometric description of the ground state of the system. Okay, so let's do something with it. Okay, let's do something more exciting. So we now have the ground state, So the ground state will have to solve some equations. I want also dynamics, right? So there will be some classical theory of gravity, which will have ADS as a solution, but there will be some dynamics, right? So the dynamical content of the gravitational theory will be a metric. Yes, you will need one. And there will be scalar fields. There will be vector fields. They can be also higher form fields. You're supposed to take UV complete theories of gravity, you know, like theories that come from low energy limits of a consistent theory of gravity, like string theory, for example. And when you do that, you will get all these extra fields. They have to be there. But for this talk, let's focus on simple theories which just have, you know, simple matter content. Now, ADS, as a solution of Einstein's equation, basically just solves this very simple equation. It is an Einstein space, which tells you that the Ricci tensor that you can compute from the metric is, there is some factor, D is the number of dimensions, or D plus 1 is the number of dimensions, and G mu nu is the metric itself. So it just solves this equation, okay? This equation has more solutions than ADS, but ADS is one of them, okay? So there is also excitations that this equation can accommodate. So let's understand a little bit what kind of problem you are solving in this kind of theories. So I will just take, you know, a simple probe, a scalar field, which solves the Klein-Gordon equation on ADS spacetime. So what are the rules of the game here? That will tell us a lot about what I can ask. So as I told you, as I tried to stress, there is a time-like boundary, okay? So when I go close to that, then the solutions of this equation will definitely have to approach something like this. So if I split, if I remove the R dependence from my field, then there will be some power of R, which is fixed by the mass of the field. And there will also be some function which is not fixed by the equations. So it's like a boundary condition. Similarly, there will be another power of R that comes with another not fixed by the equations function. And what does this mean for the field theory? Well, as I told you, scaling transformations simply scale this radial coordinate, okay? So if I take this expression and I transform it as a scalar, then what you will see is that this function phi s will scale like the source of an operator with dimension delta. And this phi v will scale like the vev of an operator with dimension delta. So the product phi s phi v gives you precisely what you would like to see. It will give you a scalar after you integrate it over R d. So the idea is then that you fix phi s, that will be like fixing a source in the field theory for the dual operator. And this phi v will be fixed dynamically for you. You have to solve the equations, be careful with the bulk, you know, whatever is happening inside the spacetime, and that will fix you the vev. Okay, so this is the main idea. I have more fields, it can become much more complicated than this, but these are the rules of the game, roughly speaking. Similarly for the metric, I mean, if I move away from ADS and I start considering dynamics, you know, there is a coordinate system that I can always write my metric like this. For the vacuum, I only had, you know, eta mu nu here, the Minkowski metric, but more generally, I can have something more general that will depend both on the radial direction and the field theory directions. Asymptotically close to the boundary, this metric, this G mu nu, will have to go like a constant metric, independent of R, plus some power that falls like 1 over R to the power D. Now, this guy, I have to fix it by hand. This will be the metric on which the field theory lives. If I want my field theory to live on Minkowski spacetime, fine, I will fix this to be the Minkowski space. If I want to have something slightly different or sources for my metric, you know, I might want to source the stress tensor, for example, I will have to introduce perturbations basically on the boundary, or I will have to deform the boundary of the theory. The boundary, which is the background for my field theory. So gamma mu nu will fix the field theory metric. Similarly, if I have a gauge field, in the bulk, that corresponds to a current from the dual field theory point of view. And a gauge field will go like some function independent of the radius. And this vector now basically fixes the sources for some conserved current J mu. Okay, so using this, I can introduce electric fields, chemical potentials, and all these nice things that you might want to introduce to your field theory. So what does holography do then? So it tells you that, okay, take the gravitational theory, compute the partition function in the bulk. You have fixed all these boundary conditions. Okay, so your partition function will then be a functional of these boundary conditions. And holography tells you that this is precisely the partition function of the dual field theory. Okay, so you can take now your partition function, you can compute functional derivatives with respect to your sources. And if you have some random scalar operator and you take its functional derivative, the functional derivative of your partition function, you will compute the value of the scalar. If you do it with the boundary conditions of the metric, you will compute the value of the stress tensor. If you do it with the sources for your current, you will compute the value of your current. Now, a small detail that I didn't tell you. So I am in a semi-classical limit. So the bulk partition function collapses to the action, to the classical action. Okay, so in that limit, if I compute the free energy or the log of S, I should be having the log of Z, the generating function here. And if I take the log in the semi-classical limit, I'm ending up just with a classical bulk action. And now, if I do this computation, you will see that these derivatives basically are completely fixed by these extra constants of integration that I had in these asymptotics. Okay, so these constants that are fixed dynamically by solving PDEs will determine the basic ingredients to determine these terms. So how can I think of RG flows now? So the simplest RG flow that you can think of is take some UV theory, deform it with a relevant scalar operator, which does not break any of your space-time symmetries. It's just a constant on your field theory side. And if it is a relevant operator and your theory flows smoothly to some infrared fixed point, then you should be able to holographically or geometrically realize this whole RG flow. So how can you realize it? So I'm writing down this action. We were not going to solve these equations. Why am I writing down this? So as I told you before, ADS is a solution of this equation, okay? So all I need is some kind of cosmological constant for the existence of ADS. Now, if I have an extra scalar in the theory, that will be dual to this operator that I will use to deform the field theory. So I have a potential here. Now the extreme of that potential fixes the cosmological constant. Okay, so the value of V at the extrema basically fixes the cosmological constant. Now if I have two vacua for this V, I can think of them as a UV fixed point and as an infrared fixed point. If I expand V around this vacua, that will fix me some masses for this phi. And as I told you, the masses fix the conformal dimensions of the dual operator. So we'll have two vacua with some operators that have different dimensions around each vacuum. So I'm basically looking for a flow between these two ADS solutions, like a domain wall solution, on which we'll have a non-trivial profile. So if if V has two extrema, something like this and like this, that would be the UV fixed point, that would be the IR fixed point. And I can easily imagine that I can basically flow from one to the other. So from the bulk point of view, what am I doing? I have an infrared ADS. This was the picture I drew. I have a UV ADS, and I'm basically gluing the two together. Okay, so that is the extra radial direction. The metric that I would have to write down should be slightly more general than ADS. It will have to accommodate this domain wall solution. I'm not breaking Minkowski. I'm not breaking Lorentz symmetry, so I should better keep this part of the metric, and the non-trivial information will be carried by this function U of R. And in order to realize this RG flow, in the small r limit or in the infrared limit, U of R should take this form. If I didn't have this extra dots here, that would be just the ADS solution for the IR. In the UV, as R goes to infinity, U of R should asymptote again like an ADS solution plus small corrections, but with a different scale, with a UV scale. So if you manage to solve the equations, you will get some ODEs. If you manage to solve these equations and find such a solution, you will have realized an RG flow holography. Now, the RG flow that I wrote here is very simple, super simple. It doesn't break any of the Lorentzian symmetries. I assumed there is no spontaneous symmetry breaking. But holographically, we have realized more general IR fixed points. Okay, I don't want to talk too much about this, but you can also realize this. You can realize Lifshitz scaling, hyperscaling violation, anisotropic scaling, or you can even find ground states which have broken translations. What about the thermal states? Now, the extra step is how do you introduce finite temperature? So finite temperature, from the bulk point of view, will be represented by a horizon. Okay, so I have this radial direction. I want this geometry to terminate at some point, at some horizon of finite temperature. And this will be the dual of finite temperature from the field theory point of view. Now, if you want to achieve that, you would have to remember the Schwarzschild metric from the GR in flat space. But instead of a sphere here, I will keep the spatial directions of the field from the field theory side, if I don't want to do something too fancy with these. And then I will have blackening factor, similarly to what you have in Schwarzschild, in the Schwarzschild metric. Now, what is the horizon? The horizon is the place where this Q of R, this function, will become 0. Okay. Now, if the horizon is located at R equals R plus, and you take the Euclidean version of this metric, you will find something like this very close to the horizon. And remember, I have taken T, I have performed a weak rotation. I called the Euclidean time tau. And I want to convince you, and this T, this time is actually the field theory time. Okay, so if I move to the boundary, this T is the field theory time. And for this metric to be regular at the horizon, you have to see that this R tau part is just the origin of R2, as long as I take tau to have period 1 over T. Okay, 1 over the temperature of the system. So as long as I do that, then this metric is regular. And you also see that from the Euclidean point of view, tau has the right periodicity. This is the fastest way you can think about temperature in this context. Now, what is this factor G? You might know that the area of the black hole horizon, or the area density in this case, because these horizons have a flat geometry, and the area density will be given by the volume element of this horizon. So this function G evaluated on the horizon will fix you the entropy density. So very quickly, you beat some language about thermodynamics of the dual field theory. Now, very quickly, I want to tell you that, yes, if you want to realize a solution at finite temperature and finite chemical potential, you have to go to the Einstein-Maxwell theory with a negative cosmological constant. And you will take the gauge field or the Maxwell field to asymptote to mu. If I take R very large, then I'm ending up with this constant mu, which I told you fixes the chemical potential. And that will be the most basic example that we know about the dual field, about a dual geometry for a field theory, for a conformal field theory at finite temperature and finite chemical potential. Now, this is a bit of a funny solution. because at zero temperature, you can take this u, take the derivative, evaluate it on the horizon, you can compute some temperature. If you take the temperature to zero, you will see that this still leaves some finite entropy density at zero temperature. But this might feel funny because you might think of the third law of thermodynamics. But as I will also tell you later, these are highly unstable. They are not always unstable, but there is many instabilities, classical instabilities associated with these horizons. Now, this is a very big topic, but I don't want to go there. So how does a holographic thermal state look like? You basically take your ADS spacetime. Okay, asymptotically, I'm still ADS. I'm only deforming, by small deformations. I have some sources here, some chemical potential. I'm not doing anything major. And as I move inside the bulk geometry, there is a horizon on which scalar fields become regular. They just take a constant value on the horizon. And also the horizon fixes the temperature and the entropy density of the system. And this is a good point to tell you that, if I have the asymptotic expansion of scalar fields, for example, you might notice that there could be solutions which are not sourced by anything, but they still take a wave. Okay? That would be precisely the scenario where you have spontaneous symmetry breaking. Now I'm jumping to a different topic. I want to tell you that holography can also realize spontaneous symmetry breaking. So with additional matter, these black brains that we have been discussing can develop perturbative instabilities. As I'm lowering the temperature, some of these scalars, vectors, or whatever extra I have can become unstable, dynamically unstable, perturbatively unstable. So those fields can also, the perturbation that will become unstable can also be breaking some other symmetries. It can be internal symmetries. It can be space-time symmetries. So if you follow the instability and you find a new stable black brane solution or a new solution to your system, this is how you realize spontaneous symmetry breaking in holography. So it's like a bifurcation point. Below a certain temperature, you find two different solutions for the same boundary conditions that you fix. Okay? So I don't want to talk about this too much. This is a model where you can realize symmetry breaking spontaneously. And now I want to move on to linear response. So how can you use holography to study linear response of a system? Well, the strategy is, very much what you would do in field theory. You would basically take your system, introduce a perturbative source. You would modify slightly the Hamiltonian. You introduce an external force to the system. If you're strong enough, you will compute the response, the BEV, and you can use that to compute the retarded Green's function. Okay, this is exactly, holography is made for this. You can introduce time-dependent or whatever source you want on the boundary. The BEVs of the system will be slightly moved away from the equilibrium values. This is what I naturally read from holography, the BEVs. And if I take functional derivatives of the BEVs with respect to the sources, that will compute for me the retarded Green's function. You just solve linearized PDEs for this. So you can, right. So from the bulk point of view, how do I set up the problem? If I want to do a linear response in real time, and in general, I have some kind of horizon, in order to compute the retarded Green's function, I have to impose infalling boundary conditions here. So basically, matter just falls through the horizon. Nothing comes out of the horizon. Okay? If I do that, that will uniquely fix the wave of the system. Okay, I have to do that. This is what fixes basically the wave of the system. If I do it in Euclidean time, I told you that the geometry is capping off to something that looks like R2, then all I have to do is to impose regularity at this origin, at the place where the time, like the Euclidean time, shrinks to 0. And for the real-time case, I told you that there is some horizon where stuff falls through the horizon. And this is precisely how you realize dissipation. Okay, so all the energy will fall through some kind of horizon, and it will just dissipate away. Now, how does it look like when you do the computation? If I just do it for the ground state, just ADS, no finite temperature, no anything, I'm just doing some vacuum computation, and conformal symmetry will uniquely fix the retarded Green's function. This is fixed by symmetry. You don't have to do any ADS computation. You can do the ADS computation, and you can relax that it gives you the right answer. This is just a sanity check. When I move to finite temperature, the story looks slightly different. And the interesting part is that the retarded Green's function is basically dominated by a discrete set of poles. So if I do, if I have some translational invariant background and I do some kind of Fourier decomposition, then I will have this wave vector k. I will have the frequencies omega, and the retarded Green's function has these simple poles with the positions of the poles being fixed by the wave vectors. It's like dispersion relations for these poles, okay? An infinite number of them. Now, if I want my background phase or my background state or the thermal phase to be stable, basically all the imaginary parts of these poles will have to be negative. Otherwise, if I go and do the real-time computation, I would find some exponentially growing modes, which I don't want, or I might want if I want, some kind of phase transition. But for a stable phase, all of these poles will be in the lower half plane, in the lower complex plane, the lower half of the complex plane. Now, these poles correspond to modes from the black hole point of view, which are source-free. So these poles are determined by what is called the black hole quasi-normal modes. So how does it look like? So at generic values of the wave vector, I just have a tree of poles. If I look at the complex plane and I put dots for the values of these poles, for a fixed value of k of the wave vector, then I will have something like this with nothing close to the origin. When I take k to be very small, smaller than any other scale of the system, or 1 over k to be, which is the wavelength, to be the largest scale of the system, then what naturally emerges, some of these poles will move close to the origin, and as you can imagine, these will be the hydrodynamic poles of the system. And this is how you witness the emergence of hydrodynamics from the holographic point of view. Now, this is telling you that I think this is one of the most exciting things in this talk, that you're basically studying a UV complete theory. It has everything. It has all you would ever want from a quantum field theory. But at the same time, you can do hydrodynamics in a specific limit as a corner of your theory. This is basically telling you, this is instructing you to study, the hydrodynamization of the system. When it becomes hydrodynamic, do something nonlinear and see hydrodynamics emerging naturally from the evolution of the system. So holography is a very good laboratory if you are interested in questions like thermalization, when your system becomes effectively described by a hydrodynamic description. And I think this is one of the best applications I have seen for holography. Now, what are these poles? These poles are exactly what you would expect. You would get some kind of shear mode, you would have sound modes, you would have charge diffusion, you might have Goldstone modes, other things, and you will have some transport coefficients that go together with these dispersion relations. Now, what holography does, and I will not go into details, is that you can read off these transport coefficients from just the dynamics of your black hole horizon. You take your thermal state, you look at the black hole horizon, at the values of your scalar fields and everything, and you can write, shear viscosity, bulk viscosity, conductivities, anything you can think of in terms of data that you have from your horizon. Okay. Now, one of the results, just by looking at these transport coefficients, one of the interesting results that came from holography is that for broad classes of two derivative gravitational theories, you find, I mean, no matter what you do to it, you can deform the theory, you can do flows, but what you always seem to have is that the ratio of shear viscosity over the entropy density is 1 over 4 pi, and that's for a very big class of theories. Now, what are some achievements of holography? Well, you can see the emergence of hydrodynamics from Einstein's equations. You can actually find correct versions of causal hydrodynamics if you go to higher order, especially of hydrodynamics. People using holography have argued that you actually, in some cases, need new transport coefficients if you have magnetic or vortical effects. And you can also systematically study hydrodynamics when you also have the presence of, small gapped modes, which are not exactly hydrodynamic. They have a tiny small gap. And how would this affect your theory of hydrodynamics? So this is a very systematic and good laboratory to extract or even test effective field theories. Now, if I want to move on to the story for far from equilibrium, this was all, just looking at small perturbations or motivated by small perturbations. What would I have to do for the next step? Well, not much. Okay, so the logic remains the same. So in the linear response, we were basically looking at small perturbations around the stationary black holes. When I go to far from equilibrium, basically large sources on the boundary or large effects, I have the same dictionary. Nothing changes about the dictionary. Okay, how I read off quantities, it's the same asymptotics. You will have some nonlinear solution, but okay, the same asymptotics applies. You will read off some vevs, you will set some sources, it's the same game. And the geometry now evolves non-linearly, so you would have to do a bit more work. Okay, it's not just linear PDs anymore, you would have to solve non-linear PDs. It is a big step, but conceptually you're doing the same thing. And strongly coupled dynamics becomes some time-dependent solutions of gravity with ADS asymptotics. You can ask many questions here. Some of the exciting questions that have been asked is, how does a system thermalize? What does it mean to thermalize? You can ask about the onset of an effect of a hydrodynamic description of your system, or you can even drive states very strongly and see what you can say about these nonlinear regimes. So about thermalization, and one of the interesting things you can do is that you can inject energy from the boundary point of view, where if I turn on a time-dependent source from the boundary point of view, what you're actually doing is that you're basically injecting energy inside ADS space. So the part of thermalization, so here, what am I drawing really? So this is the boundary of ADS, and I'm imagining that some kind of spherical dust shell is just falling through ADS, okay? So this space, which is still inside the spherical shell, it's very much like ADS space. It has not been affected too much by this spherical shell. What you see outside this spherical shell is now turning to, this black brain geometry that I was writing. And as your spherical shell collapses and it falls in the bulk, at some point you will have the formation, and it shrinks below a critical radius. You will have the formation of a black hole, of a black brain horizon. So this is, in broad terms, the mechanism under which your dual field theory thermalizes, right? So some kind of black hole will form, it will grow, and your state will become thermal. Now, an interesting question that you can ask is, what can I say about thermalization from a boundary point of view? Well, from the boundary point of view, you have different probes that you can test. A correlation function for a scalar. What you're supposed to do is to find a space-like geodesic inside the bulk that is hanging from the points that you're studying on the boundary. And depending on how far away these points are, and if it is a heavy operator, you will have to explore different areas of the bulk geometry. Some of these surfaces can even cross this spherical shell, and you can see memories. I mean, you can see memory of the original state of your system before you turn on these nonlinear sources. And depending on the probes that you're using, the system appears as if it is thermalizing at different time scales. So whether the system has thermalized or not depends on the kind of probe you're using. There is no specific time where you say, okay, now the system has thermalized. And I think this is a very nice picture, geometric picture of how you can understand thermalization. And one of the conclusions is that entanglement entropy is one of the quantities that will last close to thermalization. Another question you can ask is about hydrodynamization of your system. So what do I mean by effective hydrodynamic description? Well, imagine that you are doing some nonlinear calculation, and you find that after a certain time, at some fixed order in your hydrodynamic expansion, let's say your stress tensor is approximated extremely well by the constitutive relations, or it is described very, very well. Well, from that point, you are saying that your system has an effective hydrodynamic description. Now, what is surprising, and it came out of holography, is that this point can occur much before thermalization, long before your system became close to thermal, or before it reached its thermal state, long before it became isotropic. And what is more surprising is that the gradients of the local chemical potential, local temperature, whatever you want to use to do the hydrodynamic description, don't need to be small. So what we usually say is that hydrodynamics is a thermal state with small gradients or long wavelengths. This is when you necessarily have the hydrodynamic description. However, from the holographic point of view, you see that this is not necessary. I mean, this is probably a bit too strong. You could have an effective hydrodynamic description long before you reach the thermal state or perturbations around the thermal state. All you want is that all these UV modes that I showed you in the previous slides that form like a Christmas tree, they have been switched off. When that happens, then you have an effective hydrodynamic description.
Could you state in this context what's your definition of thermalization?
Say it again?
Could you state in this context what's your definition of thermalization?
Oh, thermalization is the same idea with what I would say in the previous slide, that you are close to thermal equilibrium.
But global or local?
Locally. This is not close to equilibrium.
In that case, like the gradient not being small is the same as thermalization.
Say it again?
You are saying that gradients being small is what you're calling as thermalization.
They do not need to be small.
Yeah, I mean, that's what I mean. So
Yes.
the gradients not being small is what you're referring to as not being.
Yes.
Like the second and fourth point are the same.
Second and fourth. Yes, exactly. Yes. Well, as long as I'm here, I'm not here.
What are the small compared to in this picture? I mean, what would they be small compared to?
For example, if you, okay, this is teleological, but let's say that you reach some final state, has some temperature, you're comparing to that.
I guess what confuses me is how do I make sure that I know how to distinguish between a system in a state where I have local equilibrium over small patches everywhere, and apparently this earlier state where somehow the hydrodynamic constitutive relations appear to give a good approximation to the stress tensor.
I guess you just write your system like this and you see that it solves the correct equations. That's all that goes into it.
How do I diagnose that locally everywhere I have good local equilibrium without doing exactly what you just said? Are these really two distinct procedures that I'm doing on the system?
No, you just look at its full evolution, right? From doing the full holographic computation, and you just witness that you can also describe it, to some order in hydrodynamics.
That's why I'm confused about the distinction that's being made between hydrodynamization and thermalization, and exactly how it's being made in practice.
Well, I guess your system is still evolving non-linearly, right?
Yeah.
So I guess this is where you say that I'm not close to thermal equilibrium.
But that sounds like global thermal equilibrium when you're saying it. To me, thermalization is local thermal equilibrium in this context. So that's me taking this system and looking at how large of a patch do I need to define so that I have some notion of uniform temperature inside this patch, and then can I do that in the next patch and so on.
This is similar to the previous notion of thermalization.
I'll postpone.
But all you're doing here is that you still have some nonlinear evolution with large gradients. But you can still have, solve basically, satisfy the same constitutive relations with the equations of hydrodynamics.
I'm also confused as to whether people can really say unambiguously that they haven't repackaged higher order gradient corrections inside this first order corrections that they're looking at. Because they usually only compare to first order hydro. So how do I know that they haven't mistakenly repackaged some of the higher derivative corrections inside?
Yeah, I guess it depends on how you define your transport coefficients.
You should define them from the final state and just stick to that value and not fit them.
This is the next slide, I guess. So this is Ben's paper. So what Ben has done is, okay, in the past we have studied what is called holographic lattices. So you can also break explicitly translations from boundary point of view. And that allows you to study transport because basically momentum relaxes. So one of the things that Ben has done is took one of these theories and he introduced a pulse for an electric field from the boundary point of view. And what I'm plotting here is the response of the electric current. Okay, this is the nonlinear response. And as you can see, the current is almost tracking what the electric field is doing. But this dotted blue line is the current you would get from the linear constitutive relation for the current, from Ohm's law. And the conductivity that Ben was using here is precisely what Blaise is describing. So holographically, you can write the conductivity as a function of temperature, chemical potential, other parameters. What you can also do is you can write the conductivity in terms of energy of the state and the charge of the state. So what Ben had done here is he plotted this blue curve by using sigma, or the conductivity, of the final state. So if you stopped the simulation here, let's say, what would be the energy and the charge density of the final state? So he tracked all this, and you see that it agrees pretty well with what you get from the nonlinear evolution of the system. So this blue curve is basically computing sigma as a function of the final state, of the would-be final state of the system. So I have found very impressive that seems to work quite well, and this is one of the lessons that we see from holography. I don't know whether this is general, much more general than this, but this is pretty suggestive. I think this is close to what Blaise was asking. So maybe I should conclude. So I hope that convinced you that holography is turning pretty non-trivial questions about the field theory side to something very tractable from the gravitational point of view. You have a nice geometric description of finite temperature states, thermal states, RG flows in terms of domain walls and black holes. So hydrodynamics emerges naturally from black hole horizon dynamics. So the non-hydrodynamic modes control relaxation in the far from, and they are also the transients of far from equilibrium dynamics to hydrodynamics. You can use holography to study systems with reduced symmetry. You can drive them strongly, and you can find the nonlinear response, all that within the same framework. And I think of holography as something that we can use to learn pretty good lessons about strongly coupled systems. So that's all I had to say today.
Any questions?
So you say hydro can set in before thermalization and equilibration, but so if understood correctly, that's in something like Vaidia system where eventually you do form the horizon, right? Just you see hydro before you actually see thermal equilibrium.
Even if you start from a thermal state, so what I plotted here was. So this was basically this is the time direction from the field theory point of view. This is space direction. And you take two nonlinear Gaussian pulses, you collide them. And what they have witnessed is that pretty soon after the collision, somewhere around here, the rest of the evolution follows very closely the evolution of hydrodynamics. So this is a pretty nonlinear regime still.
I see. But basically the horizon survives.
The horizon is there.
So do you think you could have hydro even if there's no horizon at all? Like something smooth?
I'm not sure how I would go about and discuss that.
Sorry?
I'm not sure how to discuss that. I mean, at exactly zero temperature. You would have to form a horizon, and then I would expect that.
Okay. Because for zero TRN, it was argued by Andrei that there is still a good hydrodynamics, but maybe that was special.
Possibly.
Hydrodynamics. It's not hydrodynamics, it's zero temperature thing.
Yes.
There are logs that he didn't compute because they appear at the next order. So it's really
that was leading order, I guess.
It's really got nothing to do with hydrodynamics.
Really?
Yeah.
Yeah, okay, one last question.
Thanks a lot for this very nice review. Two questions from, if I may, from condensed matter theorists.
Okay.
So first one, if I understand correctly, to construct the holographic dual of your theory, you need some conformal symmetry on the CFT side. But suppose I start with a particular type of conformal field theory. And what are the informations that I need to give to the holographic theory in the bulk in order to construct its holographic dual? So you mentioned at some point you need the metric on the boundary, or how to construct it systematically.
Provided that there is a bulk dual, you would basically have to tell me the geometry on which you would like to study from the conformal field theory point of view, whether you are finite temperature, any deformations that you want to introduce, and that's all you would need. The non-trivial thing is, I mean, the non-trivial part of the story is the existence of the holographic dual, of the bulk dual. If you're guaranteed that, then you can study pretty much anything you can imagine with smooth sources and.
So is conformal symmetry enough to guarantee the existence of the organ? No. Okay.
No. These are very special kinds of conformal field theories.
And second question on the hydrodynamization of the theory. Can I understand the statement that you don't need necessarily small gradients in terms of like not needing to linearize a Navier-Stokes equation for your hydrodynamic theory?
Not necessarily linearization, but small derivatives. You don't have to have small derivatives of your fields. You can have non-linear terms, but
Okay, let's thank you, Mr. again. We'll be in 15 minutes at 11:30.